Hello, this is MMI711, Sequence Models in Multimedia, and this is the first lecture. I'll start with a brief introduction to the course. First cover some administrative stuff. Then I'll briefly delve into the technical stuff and the outline of the course. Let me begin. Okay, Sequence Models in Multimedia. We will be covering various concepts related to understanding and processing of different types of multimedia sequences. What are different types of multimedia sequences? For example, a sound is a sequence, which is also a multimedia signal. A video is a sequence, which is definitely a multimedia signal because it has sound and moving picture. But we will consider images as sequences as well for the first time, maybe, because you are if you're taking this course, you have taken an introductory level deep learning course, and in that introductory level deep learning course, you have seen convolutional neural networks, and you know that they can process images. And images are not themselves sequences. I mean, when different frames come up together, they make up a video, which is a sequence. However, a single frame, is it a sequence? We will cover it as a sequence somehow. And there are other types of sequences as well. Text, for example, which is related to NLP. And sometimes there are very strange structured sequences as well, relational data like semantic knowledge bases, like graphs or your actions in Facebook. These are sequences. So how are we going to start? We are going to be starting with an overview of recurrent neural networks. In your introductory level deep learning course, you most probably have seen what recurrent neural networks are. What is the difference? We are going to delve deep into it. We are going to see what makes a neural network recurrent, and that detail, that feedback, it is called feedback loop. What does it change, and how do they process, and how to train a network when there is feedback. And for the first part of the course, we will be covering recurrent concepts. Then we will deal with more advanced sequence modeling concepts, more state-of-the-art, which are not necessarily recurrent, by the way. Okay, and what we're going to do is by introducing different sequence modeling problems, different recurrent architectural models, using different gated units or state-of-the-art architectures, we will cover mostly all fundamental concepts related to sequence modeling. Okay. And as I told you, towards the end of the course, we will cover concepts which are non-recurrent as well, because recently in the field of deep learning and NLP, some models process sequences using some non-recurrent models. When we learn what is recurrency and why it is good, we are going to switch to non-recurrent models. Okay, who can take this course? I'm expecting an introductory level deep learning course as a prerequisite. That's why if you've taken any of the courses below, actually you should have, because it asks for it during the registrations. You can take this course and you will use that information. I mean, I expect that you get a credible grade so that it shows that you understood what the concepts in the introductory level deep learning course were. Okay, I don't have to tell you this. If you have taken a deep learning course, you already are proficient in a programming environment for deep learning, which is most probably Python. If any of you would like to use MATLAB, I won't recommend it, but I won't say no. But regarding recurrent models, you will fall behind. Just know that, okay? So use it at your own risk. I'm going to be doing live codes in class, which will be all Python and PyTorch. PyTorch is the library that I'm going to use. It is not necessarily the one that you should be using. You could use TensorFlow or something else, but I'm going to provide my examples live coding in PyTorch. Okay. Good. The outline. I'll make an introduction to this course today. I'll talk about sequence problems in multimedia. Then, starting with next week, I'll quickly delve into recurrent neural networks. we will cover everything about recurrency in a neural network. Then we'll talk about gated units, the famous LSTM and its variants. Why did people need something like an LSTM? Why is it a recurrent neural network? Why is it a modified or advanced version of a recurrent neural network? What is its relation? Why? We're going to answer these questions because LSTM is actually a handcrafted design. Then we'll delve into more deep RNNs, CNN plus RNN architectures, which are widely used in action recognition or sound processing based deep learning models. Then we'll delve into recurrent encoder-decoder models. Since you've taken a deep learning course, you've heard of encoder-decoder models, not the recurrent ones. For example, in UNet or in hourglass architecture, where the encoder gets the features, where the decoder creates the output signal. This is the recurrent version. And with that, with the recurrent encoder-decoders, we will come up to the concept of attention, which the first version will be the recurrent model of attention. Then we'll talk about a non-recurrent version of attention. What is attention and why it should be recurrent or why it should be non-recurrent, which is context-based attention, by the way, which will bring us to transformers and sequence modeling without recurrent models. We'll talk about transformers. We'll talk about vision transformers, which is almost 1 year old. And by the end of the course, we'll talk about some advanced neural programming models, which are inspired by recurrency and memory in a neural network. So this is briefly the outline. Okay, grading is simple. I'll give you a homework, 1 or 2, I don't know. There'll be a midterm, there'll be a final. The nature characteristics of the midterm and final, I don't know yet. They could be in classroom, they could be take-home exams. I'm going to decide soon. It will depend on the conditions of the pandemic and the project. The strongest part. I'll expect you to complete a project, which will make the 40% of the course. This 40% will be split into a 24% report and a 16% presentation. The 16% presentation will be in classroom, presented by you. The 24% in the last week of the course, and the 16% will be a report prepared by you individually at the end of the finals. So you'll present your preliminary results or model your idea in the last week. Then you'll have 2 or 3 weeks to finalize your report and your results, and you'll give the project report to me, which is the 24% of it. Good. So sources, well, this is a very state-of-the-art subject. We come up with new papers every day. Vision transformers is October 2020. And there comes a new model every day. So I hope that you will follow these new models from various sources. The blogs are fantastic. Medium towards data science. I'll provide examples and sources from these websites. Well, there's a Coursera, famous Coursera lecture from Andrew Vangi, sequence modeling. It quite overlaps the first few weeks of our course, so I strongly recommend you take it as well. But it is a bit limited. I mean, after 3rd or 4th week, we will go beyond it. And if you really need a book, some people need it because they want to just get into the basics. I think Goodfellow's Deep Learning is a fantastic book because it covers everything formally. If you ever need a book, go and take that one because it's free on the internet and it is full. Okay, let us begin. So this was the illustrative stuff. Let us begin about technical stuff. The first thing we should understand in this course is, guys, what is a sequence? And to understand what is a sequence, we should understand what is not a sequence. Because actually that difference makes a lot of sense when you're trying to model or design an architecture for your deep learning model. We'll begin with what is not a sequence example. And it is, for example, consider a problem of predicting a health risk of a person based on multiple health parameters. So it's diagnosis. You go to a hospital, they take a blood from you, and you've got several numbers. I'm sure you have it. Lab results. There are some abbreviations you don't understand. There's a number. It says normal or abnormal. Those numbers. And you want to understand the relation between those numbers and about your condition. That's what your practitioner does actually. When you go to your family practitioner, they check those numbers and say, you're okay, you're not okay, kind of. Actually, that kind of a relation, which does not relate to any previous activity or previously collected data, will correspond to a machine learning model, which we call feed-forward, because we have the inputs, and at the output, we have a classification result. That's why the person, that practitioner, he is the feed-forward model here, or the machine learning model. When that model or the person is processing your data, for that model, a data point is completely independent of the previous input. So imagine a practitioner, there comes a patient, he looks at the numbers, and he decides that that patient is sick. He sends, oh, you're sick. Another patient comes, the numbers show that he's not sick, but practitioner says, I think you are sick because the previous patient was sick. But that doesn't make sense, right? Because it shouldn't make sense. Because for this problem, the practitioner should behave like a feed-forward neural network. The previous patient was independent to the recent patient. When the data that is input to a model is independent to another sample that will be input, in that case, that model is a type of feed-forward network. So all artificial neural networks you've learned, and simple artificial, vanilla artificial neural networks, are FNNs. Okay, so the first person's health risk is not related to the previous or the second person's health risk. It's simple. That's why I wouldn't consider that lab table as a sequence. That lab table, although sequentially ordered, that is not a sequence. That's a multidimensional vector fed to a model. So how will I understand if it is a sequence? Before that, you'll remember from your previous course that convolutional neural networks were the type of models which were feed-forward. Imagine you feed a cat image. The result will never change. How many times you feed it, it won't change. That's why CNNs are feed-forward neural networks, and the information we feed only to a CNN shouldn't be a type of sequence data, because in a sequence, sequential samples have a relation, and that relation is what we are trying to understand. Good. So that's the basic example. I like this. It's a fun example. Ask somebody, is this a cat image? Particularly this image. They would answer. I mean, what would they answer? So the answer would be yes, it is a cat image. So the first time you're asked, you answer like a feed-forward neural network because you have no prejudice about the question. If you had an initial state about the question, that initial state is 0. But when you're asked the question, you know that that person had asked you this question, is this a cat image? Imagine the same person asks the same question, showing the same image. Is this a cat image? If you're not some sort of robot, or if you're not, I don't know, Sheldon from Big Bang Theory, you would react differently. You would say, again, it's a cat image. You would say something like, again. This is not quite like an FNN. And if I increase the questions, the same questions over and over again, well, you would just make a joke, I don't know. You would say something that I'm a dog person. I just wrote some rubbish stuff here. You see, your reactions will change. How can we model this? I would model this as an internal state inside me. I had a prejudice about the question. The first time it was asked, I had no prejudice. That person is trying to learn if this is a cat image or not. Well, I would answer him. I would just very in a positive manner. Yes, that's a cat question. Because the initial state was empty. It was zero. But after that question is asked, that initial state, my prejudice about that person asking that question has changed. That person had asked me that question. I've given the answer. Why is that person is asking me that question again? A state change occurred to me. He asks again. My states are changed, but I answer similarly. Well, still like an FNN, because my states didn't change much. But after the third time or fourth time you're asking, my states will be dramatically changed. I will start to make jokes and stuff, because that's the state I carry. Which brings us to the idea of states, guys, states. So states inside me. I have states inside me. So a model which can process a sequence should have states inside it, so that when you're feeding the sequence one by one, it would process the states accordingly to reach a solution. Actually, the idea of states is not something new to the world of computer engineering. I mean, before recurrent neural networks, there is a field of computer engineering, computer science, which is called the computational theory. In computational theory, there are finite state automata machines, the Turing machine, and that stuff. They define states. And if you have taken a switching automata course or a related course, you know what a state is. So what I understand is, originally, feed-forward neural networks did not have states. You just feed the image and it gives you an answer. However, the type of neural networks we need to process sequences will require states similar to state machines or regular expressions and etc. Switching and automata stuff. Good. So if I need states inside me, that states will indicate that I can simulate some sort of history inside me. Because that I have a history of that question being asked to me. The concept of history and the concept of varying length data. This is very important. A CNN will only get a fixed size sample. AlexNet will only get 227 by 227 RGB images. But a video, for example, you don't know how long will it take. It will take. So when you're feeding a sequence, with each sequence sample, my states change. When the input sequence ends after an unknown number of sequences, I come to a state, which will be my decision. So unlike FNNs, the sequence modelers we would like to learn can process varying length data as well. So what makes a sequence model is it will have some sort of states inside it. That's why it will have a history, and it will have the capability to process varying length data. Good, simple. So in humans, unlike feed-forward neural networks, CNNs or ANNs, the output of one data point is not independent of the previous input. We are a never-ending, changing, multidimensional, crazy state machine, guys. So it's impossible to model us. But we can model some intelligent behaviors via us. I mean, it's not impossible, right? We'll soon be seeing human-like machines, so I'm not trying to say that, but we are very difficult to model. So a sequence can be thought of a list of elements with a particular order, such that the sequential order has a meaningful relation that we would want to understand. So sequence modeling is a task of modeling what comes next, or a task of modeling what that sequence would mean to us given that order. So unlike feed-forward neural networks, unlike CNNs, unlike vanilla ANNs, artificial neural networks, in sequence modeling, the current output is dependent on the previous input and the length of the input is not fixed. I think this was something you already knew if you're taking this course, but this is a very basic and fundamental and simple definition of what a sequence is. So this flying bird. I mean, if you only seen this image, this bird, or not this one, maybe this one, the sixth one. If only that image, if I asked you, is the bird flipping its wings? You wouldn't know. You wouldn't know, maybe it was just gliding. If only you had the sequence of frames, you could answer that question. So some problems need sequences. In that case, action recognition. Is it gliding or is it flipping its wings? Kind of. Good. So simply put, sequence modeling is a process of modeling, predicting, generating a sequence of values by analyzing a series of previous input values. Simple definition. And unlike FNNs or CNNs, unlike all non-recurrent models, in sequence modeling, the output depends on the previous input and sequence of previous input, and the length of the input is not necessarily fixed. It can be, but not necessarily. So in a CNN, you can say that it's a bird. So in a sequence, you can say that it's flying or flipping, not gliding, just like I said. Good. So what is this if it is not a CNN? We needed to understand the sequential data. We need to understand that this sequence has a history. We needed to process varying length data. So what is it? It is definitely not a feed-forward neural network. Feed-forwarding and recurrency, we're going to see the details, which you most probably already know in the following slides. Okay, we'll call them sequence models. I mean, we'll start with RNNs, but they will just be various types. So they will be sequence models, the things that we're going to learn in this course. So let's talk about what a sequence is. Is an image a sequence? So thought experiments. Well, traditionally, no. Because a sequence, an image is a bunch of pixels on a grid, a 2D grid. It is a 2D image. I mean, there are different types of image modalities, but I'm talking about a regular M by N image. So it is not a sequence. Maybe it's a sequence of pixels, but one pixel's value, is it related to the other pixel? Good questions, actually. These questions will lead us to the point where we will see images as sequences as well. But traditionally, they are not sequences. They are just, if you think of each pixel as an independent dimension, it's an M by N dimensional 2D signal, which makes it not a sequence. That's why CNNs work well on them, or other non-sequential machine learning models. And if you're working with a CNN, the input to the CNN model should be fixed, right? I mean, AlexNet, as I told you, can get 226 by 227 by 227. If you change the size, AlexNet will not accept it. So no history, no varying length data. Yes, images for some models can be considered as sequences. Or is it? In the following slides, we'll talk about this. Surprisingly, they can also be treated as sequences. And actually, you guys, as human beings, in your mind, treat images as sequences because you are very well optimized, intelligent machines. I'm going to get to that. Is video a sequence? Simple problem, yes. It's literally a sequence of frames. Okay, the frames have fixed length maybe, but when I say a video, do you know how long it is in time? So in the temporal dimension, it's a sequence. Is it a 10-minute video? Is it 100 frames or 200 frames? It can be varying length. And each frame is dependent to each other. Imagine each frame dramatically changing. your eyes wouldn't be able to sample it. A video is a smooth transition of frames. That's why each frame is related. Varying length data, each frame being related, definitely a video is a sequence with history of frames, and it can create varying length data. However, in your previous courses, maybe you have already worked videos with CNNs, fixed snippets of videos to CNNs. You can. But imagine you're trying to understand something. I'm going to define a problem. Will that guy ever stop? Imagine I'm recording people who are walking on the street. Will somebody stop for a moment? Well, if you take 3-second snippets, for example, and if that guy doesn't stop in that sequence, part of the sequence, you would never know. So you'll have to just track all the way each people. And you don't know how long it is. So yes, you may process videos as fixed length data as well, but in the end, for some problems, they should be treated as sequences. Good, very well. Sound, definitely yes. If you're coming from an electronics engineering background, or if you've taken Hüseyin Hoca's course, you know what sound is. It is temporally, uniformly sampled set of signals. So their values in time, the frequency of values change to create those sounds. So does it have history? Yes. If these values changed abruptly and chaotically, that would be noise. Actually, you know that noise. Whenever maybe you don't know that noise because you're a bit young. You only watch digital content now. So if a TV is connected to an analog antenna, and if the antenna doesn't have anything, you'll have the white page and a sound like sound. That's the sound of abruptly changing signals. That's not sound, that's white noise. But a regular sound is smooth because each input has a relation with the previous ones. Each sample creates a frequency which would make a specific timbre and pitch, which creates the characteristics of the sound. So it is an history, and it's varying length. 1 second of speech, 2 seconds of speech. And depending on the sampling rate, different numbers of samples. So categorically, sound is a sequence, but just like videos, you can process them as small snippets of sound. Again, for different problems, you cannot solve it. I can create any problem. You can create it, but just let me give you an example. Will the guy sneeze? You'll have to wait at some certain parts. He or she can. Okay. Is text a sequence? Well, again, yes, a very good example. There's a history between each word. I mean, if you're not Yoda, you make some nice sentences, but even if you're Yoda, there is a certain way you construct your sentences. That's called the grammar of a language, and which makes the sentence meaningful. So the sequential relation will create a history, because imagine you see this sentence as a whole, I understand. And actually in the future weeks of this lecture, we will see architectures like the transformer, which take the sentence as a whole. But for a recurrent model, imagine you are not reading it, you are hearing it. This is a meaningful sentence. They come just in an order, which makes it a sequence with a history. And it can be varying length, a 10-verse sentence or a 20-verse sentence. So that's definitely a sequence and is within the interest of this course. Good. Let's come back to the question where we asked, is image a sequence? Well, traditionally we said no, but we lied, guys. Why we lied? Because we wanted to give a simple example of what a non-sequential network should have been. However, the way we humans understand images are actually not like FNNs, not like a CNN. You have a CNN in your parts, but you do a very nice processing. Actually, we'll talk about that process because this will relate to an important concept that we are going to be covering in this course, which is called the attention. Attention is, guys, cognitive scientists have done experiments in the last half century. They had some sort of eye trackers which could track the movement of your eyes. And while they are tracking your eyes, they've shown people some images, example, this image, and collected the movement of different people's eyes. And they realized that people make a collectively similar motion when tracking an image. So your eyes will jump from parts. So it is like the first thing you see, maybe a face. Then, having known that it's a face, you know that this is a human being, it should belong to a human being with a body, right? Then you jump to its feet, maybe, because there should be a feet under a head. That's a historical knowledge you had from seeing previous images. Then you jump. And actually, they realized that we scan the images with this characteristic jumps, which is related to the content of the image. We don't do the same jumps in all images. Depending on the type of the image and the objects in the image, we do a characteristic jump. And different people do different things, but we have a collective way of doing it. That's why actually images can be considered as a sequence of these jumps. I can define images as a sequence of these jumps. If you define images as a sequence of these important points which took your attention, actually these things will relate to the concept of attention as we learned it, then you can define an image as a sequence as well. Actually, there are models like this, and we'll cover exactly the same examples for CNN plus RNN architectures in this course. Will be covered, not yet. So, what to do with the sequences? You know what a sequence is, and you know what a sequence is not. What to do with the sequences? Let's continue in the next video.